Hey guys, welcome back to the channel. Today we're going to do an introduction to turbulence modeling in Fluent, and we're going to look at the classic problem for validating CFD models, which is defined as the turbulent backward-facing step. So the problem that we're going to look at today is based loosely on the research of Driver and Sieg-Miller and their paper on flow reattachment for turbulent shear layers in divergent flow channels. This is a classic problem that's quoted in a lot of CFD applications and is used to validate turbulence modeling. So our domain is going to be defined as you see on the right here. We're going to have a 0.1 meter inlet. We're going to use a step height of 0.01 meters. We're going to have a total flow channel of about 0.56 meters and an outlet of 0.11. We're going to use air as our working fluid, and the air is going to be isothermal, so the temperature is not going to change. We're going to define the Reynolds number as 36,000, and that Reynolds number is defined with a characteristic length equal to the step height of 0.01. And so to achieve this Reynolds number of 36,000, we're going to have an average flow velocity at our inlet of about 46.78 meters per second. Our outlet condition is going to be a simple pressure outlet with P equals 0 at our outlet here. And our walls are going to be no slip and adiabatic, so no slip condition and no temperature or heat flux through those walls. So without further ado, let's hop over into Fluent and I'll show you how to get this problem set up. So now that we're in Workbench, we're going to start by pulling over our fluid flow analysis, and we'll go ahead and double click on the geometry tab and set up our geometry. So now that we're in Spaceclaim, you can see our geometry that we have here. We have our inlet on the left, we have our outlet on the right, and you can see that our flow domain is split up into a few different cell zones. These zones are going to help us with the meshing and analysis further, and I'll show you how we define these in meshing. Whenever you're working with a 2D analysis, you want to make sure that your 2D geometry is defined on the XY plane. And in this case, we're going to define the origin right at the bottom of our step, which will assist in further analysis as we move through our problem. So now that we have our geometry defined here, we can hop over into meshing, and I'll show you how to mesh this geometry. So now that we're in meshing, you can see that our geometry was carried over from Spaceclaim. There's a few things we're going to want to do when we import our geometry for a 2D analysis. We're going to select the geometry up here and look at our 2D behavior, and we're going to go ahead and change that to plane strain. So now we can go through and define some name selections of our geometry. So we're going to start by using the body select tool, and we're going to select our entire body, and we're just going to call this something general like flow domain. Next, we're going to select the edge tool, and we're going to start defining our inlets and outlets. So our inlet is going to be defined on the left here. We can go ahead and select that edge, click N on the keyboard, and define this as the inlet. And now we're going to define our outlet, and we're going to make sure we select both the edges because this entire edge is going to be our outlet. So again, click N on the keyboard and define that as the outlet. We're going to define the bottom face of our inlet here and the top face of our entire domain, and we're going to name those as walls. And we're going to define the bottom edge below our step as the lower wall. This will help us as we do analysis further to define some properties to that wall specifically. And we're going to do the same thing with the step, and we're going to define it explicitly as the step. The last thing we're going to want to do, since we broke up our domain into multiple cell zones, is we're going to define these two interior edges, and we're going to just label them as internal. And this will help further in Fluent to define these as interior edges in our domain. And I'll show you how that comes in when we get to our fluid analysis. So the next thing we're going to want to do for any turbulent analysis is we're going to want to set inflation layers to make sure that we're capturing our wall boundary correctly. So to do this, we're going to go to Mesh, we're going to Insert, and we're going to insert inflation layers. So we're going to start by defining the scope, and to do that, we're going to select all of our faces and go ahead and click Apply. And the next thing we're going to do is define the edges where we want our inflation layers on. So we're going to select the bottom of the inlet. We're going to select this edge that goes across the entire domain. We're going to select our lower wall. Then we're going to select our top walls as well. And we can go ahead and apply that to our boundary. And we're going to define our inflation by the first layer cell height or first layer thickness. And we want to define this because we want to make sure that we're achieving a y plus value of less than 1 to make sure that we're correctly capturing the viscous boundary layer for our turbulent flow analysis. You can calculate this first cell height by using an online y plus calculator or going through the hand calculation to define the y plus value. In our case, we have already calculated the first layer cell height for our problem, and it's going to be 1e negative 5. We're going to increase the maximum layers in the inflation layer to 20. And we're going to also change the growth rate to 1.3 to make sure that we're having a little bit quicker transition from our first cell height into our fluid flow. The next thing that we're going to do is we're going to define a face sizing. So we're going to go ahead and insert a sizing. We're going to select the bottom face here and go ahead and apply that. And we're going to change this size to 5e negative 4. And we're doing this because we know that most of our high gradients are going to be as the flow travels over this step, and we want to make sure this lower region and our flow reattachment point is accurately captured by the mesh. So we're going to give a little bit extra refinement to this bottom cell here. The next thing we're going to do is change our overall mesh size. So we can go ahead and select mesh. We'll come down to the element size here, and we're going to change that to 1.5 e negative 3. 1.5 3. Okay, so with everything defined, we have all of our name selections defined and our inflation and face sizing. We can go ahead and select the mesh and go ahead and click update. So now that our mesh has been calculated, we can analyze how our mesh quality looks. So we'll go ahead and check out our inflation layer here. So you can see we start with a very thin cell zone as we defined it as our first layer cell height, which gradually grows into the free stream. And you can see on this edge that we defined here, we're going to have an inflation layer on both sides of the edge to give us a little extra refinement as the flow travels over that step. As well as in this lower domain where we defined our face sizing, we're also going to have some smaller mesh elements than in the free stream here, just to give us some better capturing of that flow and the high gradients as we get that turbulent flow over the step. So with that, our mesh quality looks good. We can go ahead and move into Fluent and set up our analysis. So as we launch Fluent from Workbench, we're going to have a few settings here. As you can see, the 2D is going to be locked because we're importing a 2D mesh. We're going to select double precision to help with our round off error, and we're going to change our solver processes to 4. You can do this problem with anything from 1 to 4 or more settings, but 4 should be good and give us a pretty quick simulation time. Go ahead and click start and hop into Fluent. So now that we're in Fluent, we can see that our mesh is being displayed and was transferred over successfully from meshing. First thing we're going to want to do is perform a mesh check to make sure that we don't have any errors and make sure that all of our values look good. And we can do the same thing and evaluate the mesh quality to just make sure that we don't have any negative cell elements or any other errors in the mesh. So with those two things checking out, we can go ahead and start defining our setup and boundary conditions. So in this first page, the task page here, we're going to make sure we have the pressure-based solver type selected. We're going to be doing a planar 2D analysis, and it's going to be a steady state analysis as well. We're going to keep gravity unchecked in this case because it's not going to make a big difference to our final solution, and it's not required for this analysis. So for our modeling, we're going to go to modeling, and we're going to select our viscous model. And for this first analysis, we're going to use the K epsilon model. We're going to select realizable to use the realizable K epsilon model, and we're going to define the near wall treatment as the enhanced wall treatment. And we'll go ahead and click OK. In our materials tab, air is always the default material when you open Fluent. So we're going to keep that as it is, and we're going to use the standard properties of air with a density of 1.225 kilogram per meter cubed and a viscosity of 1.78 E-5 as well. So that all looks good. We can go ahead and close that out. And since we defined air as our standard material as we open Fluent, you will see that our flow domain also has air selected. So that all looks good. We can keep that as is. And the next thing we're going to do is define our boundary conditions. So for our outlet condition, we're going to keep it as a pressure outlet, and we can leave it at 0 pressure, and we're not going to change any settings here. We can go ahead and click apply. For our wall conditions, everything's going to be no slip and adiabatic. So stationary, no slip, and adiabatic, so no thermal or any other flux. So we'll keep that as is. And the rest of the walls we'll define in that setting as well. So now for our inlet velocity profile, we're going to do something a little bit unique. We want to make sure that our inlet profile is a fully developed turbulent flow profile. However, if we're just going to use a standard velocity inlet profile and define a velocity magnitude, we would have to capture enough of the inlet region to make sure that our flow is fully developed before it reaches the step. To do that, we would have to add almost 2 to 3 meters onto our simulation domain and essentially calculate and develop that flow profile every time we wanted to do this analysis of our backward-facing step. Because this would take valuable resources and is not inside the area of region or the area of interest for our simulation, which is the step, we're going to use an inlet velocity profile to help us define a fully developed turbulent flow profile at the inlet. To develop this flow profile, you can do it using analytical equations or using a secondary simulation. In my case, I did a secondary simulation where I took a parallel plate domain similar to our inlet condition, extended it for about 3 to 4 meters, and then gave a velocity inlet and let the flow fully develop. I then took that fully developed flow profile, saved it as a flow profile, and will now use it as the inlet velocity condition for this problem. I will have a second video linked in the description showing how to create these flow profiles for you to use in the future. So in our case, what we're going to do is we're going to go ahead and go to File, we're going to read, and we're going to read in that flow profile. And we can open our flow profile here. And so now what we're going to do for the inlet velocity, we're going to define the velocity magnitude by this flow profile. So we're going to select our velocity magnitude and go ahead and click apply. And the other thing we're going to want to do for our inlet condition is also change our turbulent inlet conditions. These turbulent inlet conditions are important to make sure that you're capturing an accurate simulation and make sure that your region of interest is achieving correct values. So in our case, what we're going to do is we're going to use the intensity and hydraulic diameter to define our inlet profile. We're going to keep the turbulent intensity set at the default value of 5%, and we're going to change our hydraulic diameter to 0.2. This hydraulic diameter can be calculated by hand with an equation that I will show on the screen now. And for the hydraulic diameter of flow between two parallel plates, it can simply be defined as 2 times the diameter or gap between those two plates. So we'll go ahead and click apply on that. And now all of our boundary conditions are set accordingly, and we can keep moving. So the next thing we're going to do is check out our methods here. For greater accuracy, we're going to use the coupled scheme for the pressure velocity coupling. We're going to keep the gradient as the least squares base. We're going to keep these on second order. For the turbulent kinetic energy and dissipation rate, we can make these second order upwind as well, just for a little bit more accuracy in our simulation. We're going to use the pseudo time step method to help achieve some better convergence, and we're going to keep this set to global time step. The other thing we want to check here is high order term relaxation, which can help again with our convergence and stabilize the simulation a little bit. Looking at our controls, we're going to keep with the default values for our relaxation factors for all of our values in here. And the next thing we're going to want to do is define some report definitions to help us monitor our solution as it's converging. So the first one we're going to define is we're going to define an area weighted average, and we're going to call this skin friction. And what we're going to do is we're going to keep area weighted average. We're going to go to our field variables and select wall fluxes. And then we're going to look at the wall shear stress. And we're going to select our lower wall and deselect report file because we don't want to actually output this graph, but we just want to keep the plot. And this is actually going to help us analyze our solution as it's converging and make sure not only our residuals are converging, but that our actual flow simulation is converging correctly. So go ahead and click OK. And we're going to define one more, and that's going to be the turbulent viscosity ratio at the outlet. So again, we're going to go to surface report. We're going to go to area weighted average. We're going to call this turb ratio. And we're going to select turbulence for the field variable, our turbulent viscosity ratio, and we're going to select the outlet. And again, decheck report file. We're going to analyze this because in a turbulent flow simulation, it can take a little bit of time for the flow variables, especially downstream from your inlet condition or region of interest, to fully converge. So this is a great value to look at as our solution is converging to make sure that our numerics are converging correctly. So go ahead and click OK on that. And with that all set up, we can go ahead and initialize. We use hybrid initialization. And we can go to run calculation. And we're going to go ahead and do 500 iterations. And the other thing we're going to want to change here is we're going to want to change our fluid timescale for our pseudo time step settings. We're going to change that to 0.4. This can help with a little bit of oscillation in the residuals and give us better convergence. This timescale factor can be calculated by an analytical equation that can be simply done by hand. In this case, we're just going to set it to 0.4. And we'll go ahead and click calculate and run our calculation. So what you can see now is we have our monitor point for our turbulence ratio. You can see how that's changing. We can also look at our skin friction coefficient, which seems to be converging pretty quickly. And we can also take a look at our residuals, which are also converging very well. So we're going to let this go out till the calculation is complete. And one thing we're going to want to note here, if we look at our residuals, it looks like our residuals are converging correctly and we hit our target for the residuals. It looks like our skin friction coefficient has converged well, showing that that has converged correctly. And if we look at our turbulence viscosity ratio, you can see that this value is still changing a little bit. So there's a little bit of slope to this line. And if we stopped our calculation here and we went and analyzed our data, we would get some error because it's clear that our flow numerics are not fully converging at this cutoff point that we defined. So to help get more accurate results, what we're going to do is go to the results tab. We're going to select residuals, and we're going to decrease this residual value to make sure that our simulation calculates for longer. So we're going to change this continuity one to 1e -6, and we're going to go ahead and click OK. And what you'll see as we start calculating again, the calculation will continue to converge, our residuals will keep going, and the calculation will not stop until our continuity, or this top blue line, reaches our target value of 1e -6. So we'll go ahead and let that calculate up to the convergence point. So now that we can hit that convergence point, we can once again check our turbulent viscosity ratio. And now you can see that our viscosity ratio has flattened out, showing that that value has converged as well. And we can be more confident that we're reducing convergence error in our simulation and we're getting accurate results. So now that our simulation is converged and our data has been collected, we can go ahead and quickly post-process in Fluent before moving into CFD Post for further analysis. In Fluent, we're just going to quickly plot a contour. So we're going to go to Contour, Plot New. We'll call this Velocity Contour. And we'll go ahead and plot a contour of the velocity magnitude. And we'll leave all the surfaces unchecked so it plots in the entire domain. Go ahead and display. And we can just quickly look and make sure that our simulation is running as intended. So we can see we are getting a good free stream velocity. We can see our recirculation of our flow over our step. And we can see that our inlet profile was captured correctly. So all the data looks good. And we can now close out of Fluent and move into CFD Post. Now that we're in CFD Post, we can start doing some more quantitative analysis of our simulation data. We're going to start by replotting the contour that we previously plotted in Fluent. So we'll go ahead and insert a contour. We'll call this velocity contour. And we're going to select the symmetry as our domain. We'll select velocity. We'll leave the range on global and we'll increase the number of contours up to 50. Go ahead and click apply. So we can see our free stream velocity, we can see our recirculation over our step, and we can get a general sense of what our flow field looks like. The next thing we can do is plot another contour. In this case, we're going to plot the turbulent kinetic energy. We'll call it turbulent K. We will again select the symmetry as our domain. We're going to select turbulent kinetic energy and leave the range on global and increase the number of contours up to 50. We'll shut off our velocity contour and we can now look at our turbulent kinetic energy. So as you can see, as expected, as the flow moves over our backward facing step, we're getting a lot of turbulent kinetic energy as the flow recirculates and then reattaches along our lower wall. So to get a better sense of what our recirculation zone looks like, and analyze where our reattachment point is, we can plot some velocity vectors. We'll go ahead and select the vectors. We'll call this velocity vectors. Okay. Again, for location, we'll select the symmetry face. Click OK. We'll leave the sampling on vertex. We're going to increase the reduction factor a little bit to reduce the number of arrows or vectors that we have. We'll increase that to 4. Leave our variable's velocity and we'll leave our projection on nothing. The only other thing we're going to want to change here is we can change our symbol size. So we're going to normalize all the symbols. So even the small velocity arrows are going to be a little bit larger and a little bit easier to see. And we're going to decrease our overall symbol size to about 0.05. Go ahead and click apply. Again, we'll turn off our contour plot and we can take a look at our velocity vectors. So what we can see here is as our flow travels over our step, we're getting the recirculation of our flow below that step. And we can get a rough sense of where our recirculation point is, where our flow starts moving once again in the streamwise direction along that lower wall. To get a better sense of where that reattachment point is, we're going to actually plot a quantitative XY plot, and we're going to use that to compare some experimental data. So the first thing we're going to want to do that validation between our experimental data is we're going to want to make our X dimension non-dimensional. To do that, we can create an expression. We can go to right-click, New, and we're going to call this X step. Click OK. So what we're going to do is we're going to take our variable for the X axis, and we're going to divide that by our step height. So in this case, I'm going to write it in explicitly as 0.01. Don't forget your units and click apply. And to be able to use this expression in a chart, we're going to have to create a variable. So we'll go to the variable tab, right click new, and call this x step vary. Okay. And for our method, we'll leave it on expression. And on the expression here, we'll choose our x step expression that we just created and click apply. So now what we can do is we can go ahead and insert a chart. We'll call this wall shear chart and click OK. We're gonna plot a scatter chart. We'll give the chart a title. And we'll go ahead and move over to our data series. So our first data series, which is going to be our simulation data, we'll title it as sim data. And we're going to select our location as the lower wall. For our x-axis variable, we're going to select the non-dimensional x variable that we created. So we'll select our x step variable, click OK. And for the y-axis, we're going to do the wall shear stress in the x direction. So we'll select wall shear X and click OK. And we can go ahead and apply that and see how our data looks. So the most important variable that we're looking for here is the zero crossing or the second zero crossing in our wall shear stress. This zero crossing point corresponds to our reattachment flow, or where the flow again starts moving in the streamwise direction. The negative value here refers to the recirculation that we saw below the step. And the next thing we're going to want to do is we can pull in some experimental data to validate our simulation and see how well our turbulence model is capturing the real life phenomena. So to do that, we can go back to the data series tab. We can create a new data series and we'll call this experimental data. And we're going to actually pull in a file or a CSV of that experimental data. This data is publicly available, and I'll have a link to the description for you to find this data and pull it into your own model. We're going to go ahead and select our CSV for our wall shear. Go ahead and click open. We'll leave the x variable or x-axis as column 1, y-axis as column 2, and we can go ahead and click apply. So what we can see here is that we're getting fairly good agreement between our experimental data and our simulation data. And again, the most critical point that we're going to use to validate our model here is going to be the reattachment point. So if we look at the blue squares, which is our experimental data, we can see roughly where our reattachment point is in our experimental data. And we can see that it's very close to our experimental data. So we're getting very good agreement between our simulation and experimental data. So from here, you can keep analyzing your problem. You can plot some more XY plots of pressure contours, of velocity as the flow moves over the step, or anything else that you want to do to validate both your simulation and validate that against experimental data. But I think for the purpose of this tutorial, we're going to leave it there. So in this tutorial, we took a little introduction into turbulence modeling in Fluent, and we were specifically looking at the backward-facing step problem and validating that to some readily available experimental data. I would highly suggest at this point, you go back and you start experimenting with some more turbulence modeling in Fluent. A great thing to do would be to try a different turbulence model and see how it agrees both to the K epsilon model that we used in this experiment or in this tutorial, and also see how it agrees with the experimental data. You'll find that one turbulence model may be more accurate for the simulation that you're trying to do. And it's always a good check to try a few different models if you're trying to get really accurate results for your simulation. This tutorial and this problem of the backward-facing step is also a great problem to try out a mesh sensitivity or mesh refinement study. For the mesh refinement study, you can use the reconnection point as your critical parameter for your mesh refinement, and you have very good experimental data to validate that point to, and make sure that you're achieving mesh independence for your problem. So with that, I would like to say thank you for watching, and don't forget to like, share, and subscribe to the channel. Thank you.